Kepler's laws and the motion of planets. So Kepler has three laws that describes the motion of the planets. The first one is that all planets move in elliptical orbits with the sun at one focus. So if this is our ellipse, you can see that an ellipse has two focus points, and the sun is at one of these focus points, and the motion of the planet is in an elliptical orbit around this focus point. Number two, the radius vector drawn from the sun to a planet sweeps out equal areas in equal time intervals. So that is, if you draw a radius vector here from the focus point to the planet, you will see that it sweeps out equal areas in equal time intervals. And number three, the square of the orbital period of any planet is proportional to the cube of the semi-major axis length of the elliptical orbit. Remember, semi-major axis length is this length here, so it's the long axis. Half of the long axis length is the semi-major axis length. Okay, so we will look at these laws in more detail. So let's start with Kepler's first law. So first of all, what is an ellipse? So if we have two equidistant points from the y-axis located on the x-axis, and let's label them as focus points, an ellipse is defined by r1 plus r2 is a constant. So r1 is the radius vector drawn from focus point 1, and r2 is from focus point 2. So their sum must be a constant. So this is what defines an ellipse. So f1 and f2 are focus points. So for the long axis of the ellipse, the half of the value, half of the long axis value is a. So that's the distance from the origin to the end point of the ellipse on the x-axis. That is the semi-major axis length a. And for the short axis, if we go from the origin to the point on the ellipse, that's point B here, we have the semi-minor axis length b. So this minor axis is 2b and major axis is 2a. Alright, so 2a is major axis length, 2b is minor axis length. So remember that r1 plus r2 is a constant, so let's concentrate on these points a and b. So for point A, what is r1? So r1 is the distance from the focus point 1 to point A. So as you can see, if I were to go from this point to point A, that distance would be 2a. But if I go from a focus point 1 to point A, because the focus points are at a distance c from the origin here, so you can see that this distance is c for focus point 2, and this distance is also c for focus point 1. So we go a distance c, and then we go a distance a, semi-major axis length, to reach point A. So r1 is c plus a. What is r2? Now if I go a distance a from the origin to point A, and if I subtract c from it, that would be a minus c, so r2 would be a minus c. So what is r1 plus r2? r1 plus r2, c plus a minus c, it is 2a. So r1 plus r2 is a constant, is actually r1 plus r2 is equal to the twice the semi-major axis length. So that is what defines our ellipse. So if you look at point B here, so you can see that I'm going to find a right triangle. So this is this distance is c, this distance is the semi-minor axis length b. So the distance from focus point 1 to point B would be the hypotenuse of this right triangle. So I would have this right triangle here. So you can see I go from here to here. All right, so this is my distance r1 from focus point 1 to point B, and that is basically a part of this right triangle. So this is the hypotenuse of this right triangle. So it would be b square plus c square is equal to r1 square. So r1 is square root of c square plus b square, and r2 is also square root of c square plus b square, because they are basically symmetric with respect to this point. So these two distances should be the same. All right. So from these observations, now you can see that since r1 plus r2 is equal to 2a, r1 plus r2 is also equal to twice square root of c square plus b square. A square is equal to b square plus c square. So that's basically what defines the ellipse. Semi-major axis length square is semi-minor axis length square plus the distance from the origin to the focus point part, the distance c squared. Okay. Now, in order to define the shapes of the orbits, we talk about the eccentricity. The eccentricity of an ellipse is defined as the ratio of the focal length c to semi-major axis length a. So c, remember, is square root of a square minus b square. So it is square root of a square minus b square divided by a. That is the eccentricity. For a circle, c is equal to 0. So if c is equal to 0, a square is equal to b square is equal to r square. And that gives us an eccentricity of 0. For a long, thin ellipse, we have a much greater than b. So this can be ignored. So you can see that square root of a square over a turns into 1. So eccentricity of 1 defines a long, thin ellipse. For the Earth-Sun system, the eccentricity is rather close to 0, 0.017. For the Mercury-Sun system, it is more elliptical, 0.21. So you can see that the Earth-Sun orbit is closer to a circular orbit. Now, when we look at a planet in orbit about the Sun, so this is our Sun at focus point 2 here, and the planet is located at a maximum distance from the Sun. So what is the distance between this planet and the Sun? It is the semi-major axis length a plus the focal length c. So d is equal to a plus c. That's called the aphelion position. And if we put the Earth at our focus point f2, and we're looking at a satellite or some meteor or something that is orbiting around the Earth, you will see that this is going to be apogee instead of aphelion. So helion is for the Sun, the g is for the Earth. Okay, so aphelion and apogee define the maximum possible distance in the elliptical orbit from the focus point. Now, if we have the planet at the closest possible distance in the elliptical orbit to the Sun, that distance would be a minus c, the semi-major axis length minus the focal length c. This would be called perihelion position. And if this is not Sun but the Earth, and we're looking at the satellite that is orbiting around the Earth, then this would be perigee. So perihelion and perigee are the closest possible positions to the Sun and to the Earth, respectively, in the elliptical orbit. Now, for unbound objects that are not really part of this elliptical orbit, for example, meteors that pass by and never return, etc., we have eccentricity equals to 1, exactly equal to 1, that defines a parabola. So remember that long thin ellipse is basically this limit, and that long thin ellipse actually turns into a parabola for an eccentricity exactly equal to 1. Eccentricity greater than 1 defines a hyperbolic path, and eccentricity equals infinity defines a straight line. So you can see more information about eccentricity of the orbits on this website. All right. Now, Kepler has a second law, which states that if you draw a position vector of the planet from the sun and look at the areas that are spanned in equal time intervals, this would be a constant. So dA dt would be a constant. So let's see how that works. We can look at the gravitational force, and we know that it's a central force. So the gravitational force about the pivot point will have no torque effect because it's pointing towards the pivot point. So the torque on this object that is feeling the gravitational force is r cross fg, and since r and fg are in the same axis here, they would have a zero cross product. But since the net external torque on a system defines the rate of change of angular momentum, that's Newton's second law, torque equals dl dt. And for example, if you remember, for rigid objects, the angular momentum was I omega, moment of inertia, times angular speed, and torque equals I alpha, was Newton's second law. Okay, so if we have no torque acting on this system, then the change in angular momentum is zero. The angular momentum should be a constant of this motion. Okay, so if I look at the radial position vector of this object that is in the elliptical orbit about the sun at focus point 1, let's say, and when I look at the change in the position vector for a time interval dt, v dt will be the displacement vector on the elliptical orbit. And the area that is spanned by the r vector here would be called dA. Now, the angular momentum is r cross p, r cross mv. So that's the mass of the planet times r cross v, and this is a constant. Let's call this constant L. And what is this area? So if you think about this parallelogram that is defined by this dr vector and r vector here, the area would be 1/2 the magnitude of r cross dr. So that's how we can calculate this area spanned here. And the r vector is v dt. So I know that r cross v is L divided by mass of the planet. So that would be L divided by 2 mass of the planet times dt. And you can see that dA dt is L divided by twice the mass of the planet, and that is a constant. So the area vector that is basically swept out by drawing the radius vector from the sun to the planet, basically this sweeps out equal areas in equal time intervals. dA dt is a constant of the motion, and that is a straight consequence of angular momentum conservation for this system, and that is linked to the fact that gravitational force is a central force with no torque effect. Okay, so the radius vector drawn from the sun to any planet sweeps out equal areas in equal time intervals. And as I mentioned, since this is a result of the fact that gravitational force is a central force, it is true for any situation involving a central force. Finally, we have Kepler's third law, which talks about the period of the orbit. So let's demonstrate this for a circular orbit. Here's our planet. This could be our Earth. Remember, the eccentricity is rather low. It's very close to a circular orbit about the sun. And the gravitational force is basically the central force this planet feels. It's mass of the planet times the centripetal acceleration. So the gravitational force, Newton's universal law of gravitation, gravitational constant g, mass of the sun, mass of the planet divided by r squared is equal to mass of the planet times the centripetal acceleration v square over r. So these r's will cancel, mass of the planets will cancel. So for periodic motion we have v, for the uniform circular motion of the planet here, it's 2 pi r, the circumference of the circle divided by the period t. So we can substitute that for v here. So we see that g m sub s over r is v square, 4 pi square r square over t square. So if we take t squared to the left hand side and take the other terms to the right hand side, you can see that r times r squared gives us r cubed. We see that t squared is a constant that belongs to the sun, because there's mass of the sun here, multiplied by r cubed. Okay, so what is this constant for the sun? It is 4 pi squared divided by 6.67 10 to minus 11 universal gravitational constant, 1.989 10 to 30 kilograms mass of the sun. So this gives us 2.98 10 to minus 19 seconds square over meter cube. Now, how would we modify this result for elliptical orbits? For elliptical orbits, we replace the radius with the semi-major axis length a. So t squared is equal to ks times a cubed. So this is a more precise answer for the elliptical orbits. Okay, so let's take a look at an example. Calculate the mass of the sun, noting that the period of the Earth's orbit around the sun is 3.156 times 10 to 7 seconds, and its distance from the sun is 1.496 10 to 11 meters. Okay, so we want to calculate the mass of the sun. We know that the period is 3.156 times 10 to the 7 seconds. The sun-Earth distance is 1.496 times 10 to 11 meters. And for this orbit, the eccentricity is very low. We know that it's approximately a circular orbit. So we can write basically the gravitational force, the gravitational constant g, mass of the Earth, mass of the sun divided by the distance squared, d squared, is equal to mass of the Earth times v square over r, which is v square over d. Now you can see that we will have the mass of the Earth cancelling here, and for v we will substitute 2 pi d divided by the period t. So this is going to become, so let me take this a little bit far away here. This is going to become 4 pi square d square divided by t square d. Now I have a cancellation of these, one of these here, and now you can see that I have g ms over d square equals 4 pi square d over t square. So if I isolate mass of the sun from this, mass of the sun is basically equal to 4 pi square d cube divided by g t square. So let's substitute the numbers here. We have 4 pi square 1.496 10 to 11 cube, 6.67 10 to minus 11 meters times the period square, 3.156 10 to 7 squared. So this will give us an answer for mass of the Sun, 1.99 times 10 to 30 kilograms. All right, so this is our answer. Now, what was the actual value? The actual value is a little bit off, 1.989 times 10 to 30 kilograms. And what is the difference due to? Well, we have assumed that it's a circular orbit, but it's actually an elliptical orbit with a low eccentricity. So rather than being strictly a circular orbit. Okay, another example. Consider a satellite of mass m moving in a circular orbit around the Earth at a constant speed v at an altitude h above the Earth's surface as illustrated in figure. So this is at a distance re plus h in a circular orbit around the Earth. Determine the speed of satellite in terms of g, h, and radius of the Earth and mass of the Earth. And part B, if the satellite is to be geosynchronous, that is appearing to remain over a fixed position on the Earth, how fast is it moving through space? Okay, now mass of the satellite is m, speed is v, altitude from the Earth's surface is h. So let's start with part A. This is performing uniform circular motion. The gravitational force, as you can see, is the central force, centripetal force, which is the gravitational constant g. We have mass of the Earth, mass of the Earth, mass of the satellite divided by the radial distance squared, which is re plus h squared. So this must be equal to mv squared over r. So this will be mv squared over re plus h. So that is basically the distance from the center to the position of the satellite in the circular orbit. So what does that give us for the speed of the satellite? You can see here we have one of the re plus h's disappearing and the mass disappearing from both sides. So we obtain v is equal to g times mass of the Earth divided by re plus h square root. Okay, so this is our answer to part A. Now part B. Given that this is a geosynchronous orbit, how fast is it moving through space? Once again, the geosynchronous means it's synchronized with the Earth's spin about its axis. So the period of rotation is 24 hours, which is 24 times 60 times 60, 86,400 seconds. So the speed is 2 pi re plus h divided by the period t. So if we let re plus h equal to r, then we see that 2 pi r divided by t is equal to square root GME over R. So we obtain R cube is equal to GME over 4 pi square T square, which is basically Kepler's third law. So if we substitute the numbers, R is equal to G 6.67 10 to minus 11 the period squared. The period is 86,400 seconds, so it is 86,400 seconds squared times mass of the Earth 5.97 10 to 24 kilograms divided by 4 pi square to the power 1/3. So this gives us 4.22 times 10 to 7 meters. Now what is the corresponding speed? It is 2 pi r divided by the period, which is 2 pi times 4.22 10 to 7 meters divided by the period 86,400, and that gives us a speed of 3.07 times 10 to 3 meters per second. Okay, so this is our final answer. And finally, we can talk about the gravitational field. And this is basically another interpretation of the gravitational acceleration. An object of mass m creates a gravitational field at every point in space such that a test particle placed at a certain point feels an attractive force which is equal to the mass of the test mass multiplied by the field. So here is the idea. Capital M creates a field, and this field interacts with a mass m and causing a gravitational force. So if this is our capital M, you can see that there is a gravitational field created around it, and that's a central field. It's pointing towards the center of this object. If I put a test mass here, it's basically going to feel a force, which is the mass multiplied by the field that this object creates. This is called the principle of action at a distance. The gravitational force is mass times the gravitational acceleration. Gravitational acceleration is gravitational force divided by m. And remember that this gravitational force is gm product of the masses divided by r square in minus r hat direction, pointing towards the center. So gravitational acceleration was minus gme over r square r hat for the Earth's object system, and therefore this is our gravitational field. Basically, this is gravitational field multiplied by the test mass gives us the gravitational force. So that's the action at a distance. You will see the same thing for electricity as well. A charged object creates an electric field, and when you bring a test charge in that electric field, it's going to feel an electrical force through interaction with the field. So there is a cause, which is the main object that creates the gravitational field, and there is the consequence by interacting with this field with a test mass. And that's the same principle applies to electricity. A distribution of charge creates an electric field, and you have a test charge that's going to interact with this field and feel a force as a consequence. Okay, so now to summarize, in this lecture we have talked about Kepler's laws. We know that all planets move in elliptical orbits with the Sun at one focus point. We talked about that ellipse. The ellipse is defined by the distance from the focus points F1 and F2 being a constant, and that constant we have seen is equal to twice the semi-major axis length A. And we also see that by looking at the distance from the origin to the point B, which is our semi-minor axis length, we have this right triangle forming that shows us that A squared is equal to B squared plus C squared. Well, if you have C is equal to 0, A squared and B squared are the same. So C is equal to 0 means the focus point is the center point. That is a circle. A squared equals B squared equals R squared. And that corresponds to an eccentricity, which is the focal length divided by the semi-major axis length A of 0. For a long-thin ellipse, we see that the eccentricity approaches 1. And when eccentricity is exactly equal to 1, it turns into a parabola. The Earth-Sun system eccentricity is rather low. It's approximately a circular orbit. Mercury-Sun systems, you can see it's a larger eccentricity, more elliptical orbit. If on this elliptical orbit we are at the farthest distance from the Sun, that's called aphelion. If we are at the farthest distance from the Earth at the focus point here, it's called apogee. If we are at the shortest possible distance, it's called perihelion from the Sun. From the Earth, it would be called perigee. So this basically concepts will appear in some problems, so you should be familiar with aphelion. Up means farthest, peri means closest. For unbound objects, the other possible eccentricities are 1 equals to gives us a parabola, greater than 1 turns into a hyperbola, and infinite gives us a straight line. Kepler's second law states that if we draw a radius vector from the Sun to a planet, this vector will sweep out equal areas in equal time intervals. We have seen that this is a consequence of the fact that the angular momentum for this system is conserved because there is no external torque, and there is no torque in this system because the gravitational force is a central force, and this result is valid for any situation that involves a central force. And if we write this angular momentum r cross p, and we know that the area of a parallelogram is basically the magnitude of r cross dr, so this would be half the area, so it's 1/2. We see that this constant is L divided by twice the mass of the planet. And Kepler's third law is basically about the period of the orbit. The square of the orbital period of any planet is proportional to the cube of the semi-major axis length of that elliptical orbit. We have shown that for a circular orbit, equate the centripetal force, the gravitational force, and we see that the period t square is ks, the k constant that belongs to the Sun, which is 4 pi square over g times mass of the Sun times r cube. And for an elliptical orbit, we replace r with the semi-major axis length a. And we looked at two examples, basically examples that show the application of Kepler's third law. We look at the Sun Earth system, and by knowing the period of the orbit and distance from the Sun, we can calculate the mass of the Sun. We see that the answer we get is a little bit different from the actual value, but this difference can be attributed to the fact that it is not an actual circular orbit, but it's an elliptical orbit. And then we talked about a satellite in a circular orbit around the Earth. We can basically look at the gravitational force as the central force and determine the speed. And knowing that this is a geosynchronous orbit, that means the period is 24 hours, we can substitute that into V. 2 pi r divided by the period is our speed. And we know that the radius cube is proportional to t square. This is now a constant of the Earth, or t square is equal to ke times r cube. That would be Kepler's third law. We can calculate the radius, and then we can calculate the speed. And then finally, we talked about the concept of gravitational field, which is another way of looking at this gravitational force. Gravitational force comes from the interaction of a test mass with the gravitational field created by an object. That's called action at a distance. And this gravitational field is precisely equal to our gravitational acceleration, Fg divided by m.